Comparing empirical probabilities and classical probabilities. We just saw that the classical probability of rolling a 7 is 1 out of 6, which is approximately 0.167. Suppose a pit boss at a casino rolls a pair of dice 100 times and obtains 15 sevens. From this empirical evidence, we would assign the probability of rolling a 7 as 15 over 100, which is equal to 0.15. Now, if the dice are fair, we would expect the relative frequency of sevens to get closer to the 0.167 as the number of rolls of the dice increases. In other words, the empirical probability will get closer to the classical probability as the number of trials of the experiment increases due to the law of large numbers. If the two probabilities do not get closer, then we may suspect that the dice are not fair. In simple random sampling, each individual has the same chance of being selected. Therefore, we can use the classical method to compute the probability of obtaining a specific sample. So in this next example, we're computing probabilities using equally likely outcomes. Now, Sophia has 3 tickets to a concert. But Yolanda, Michael, Kevin, and Marissa all want to go to the concert with her. Now, to be fair, Sophia wants to randomly select the 2 people who will go with her. So for part A, we're going to determine the sample size of the experiment. In other words, we're going to list all the possible simple random samples of size n is equal to 2. So the first one we can say is, we can pick Yolanda, and then Michael. And then we can also say Yolanda and Kevin, and also Yolanda and Marissa. And we also have Michael and Kevin. We also have Michael and Marissa. And then Kevin and Marissa. Okay, so what this tells us is the following. This gives us the following table here. So we have Yolanda, Michael, Yolanda, Kevin, Yolanda, Marissa, Michael, Kevin, Michael, Marissa, and then Kevin, Marissa. So now what we want to do is we want to compute the probability of the event that Michael and Kevin attend the concert. So we want to compute when Michael and Kevin attend a concert. So that means that we have Michael and Kevin listed here. Okay, now how many possibilities do we have? Well, because each outcome is equally likely, the probability of an event is the number of outcomes in the event divided by the number of outcomes in the sample space. So in the sample space, we have a total of 6 because we have 6 choices to choose from. 1, 2, 3, 4, 5, 6. And there is one way the event, okay, in this case, Michael and Kevin attend a concert can occur. And so we see that there's 1. So that means that there's, therefore, the probability that Michael and Kevin will attend the concert is 1 out of 6. Okay, now we want to compute and interpret the probability of the event that Marissa attends the concert. So again, because the outcome is equally likely, the probability of an event is the number of outcomes in the event divided by the number of outcomes in the sample space. And we're going to interpret the probabilities using a relative frequency approach. Okay, so again, we have a total of 6 in the sample space. And there are how many ways the event that Marissa attends the concert? Well, we can see that Marissa attends the concert. Here is 1 time, 2 times, and then 3 times. So therefore, the probability that Marissa will attend is 3 out of 6, which then becomes 1 over 2, which represents 0.5, which is equal to 50%. So if we conducted this experiment 100 times, we would say about 50 of the experiments would result in Marissa attending the concert. Okay, next example is that we're comparing the classical method and the empirical method. Now, suppose that a survey asked 500 families with 3 children to disclose the gender of their children and found that 180 of the families had 2 boys and 1 girl. We want to estimate the probability of having 2 boys and 1 girl in a 3-child family using the empirical method. Okay, so we're going to determine the relative frequency of the event 2 boys and 1 girl, because that's what it's asking. We want to estimate the probability of having 2 boys and 1 girl in a 3-child family. So we're looking for 2 boys and 1 girl. Okay, now the empirical probability of the event, E, which is equal to 2 boys and 1 girl, is the following. Okay, the probability of event E is the relative frequency of event E. Well, we know that there's 180 of the families had 2 boys and 1 girl. So 180 of the families had 2 boys and 1 girl. And we're going to divide it by the amount of families that were included, which is 500 families. So we're dividing that by 500, which is going to give us 0.36. So then we would say the following. We would say that there is about 0.36 probability that a family with 3 children will have 2 boys and 1 girl. Okay, now the next question says we want to compute and interpret the probability of having 2 boys and 1 girl in a 3-child family. Now using the classical method. We use the empirical method for the first part. Now we're going to use the classical method and assuming boys and girls are equally likely. Now we need to count the number of ways the event 2 boys and 1 girl can occur and divide this by the number of possible outcomes for this experiment. Now, to determine the sample space, we're going to construct a tree diagram to list the equally likely outcomes of the experiment. Now, to construct a tree diagram for this situation, we're going to draw 2 branches corresponding to 2 possible outcomes, a boy and a girl, for the first trial, which would be the first child. So that means that we have 2 branches here. Okay, one that represents a boy and the other one that represents a girl. Okay, and then for the second child, we're going to draw 4 branches because we have 2 branches for this one, which would be a boy or a girl, and then 2 branches for this one, which also represents a boy or a girl. Okay, and then we're going to have to do another set. So that means that this one's going to represent 2 branches, which is a boy or a girl. And this one is also going to represent 2 branches, which is a boy or a girl. And this one also represents 2 branches, which is a boy or a girl. And then this one as well, which is a boy or a girl. So now, why do we stop here? Well, because the event is asking us for 2 boys and 1 girl, which means that we want 3. So therefore, if we take a look at this here, we have 3 boys. So that means that our first one of our sample size is going to be 3 boys. Okay, the next one is going to give us the following. We're going to look at boy, boy, and then girl. So the next one is going to represent boy, boy, and then girl. Okay, and then the next one is going to be boy, girl, and then boy. So therefore, we have boy, girl, and then boy. Okay, and then what else do we have? We have the following. We have boy, girl, and then girl. And then you can see with the next one, we have girl, boy, boy. So here you can see that we have girl, boy, boy. So girl, boy, boy. And then the next one is going to be girl, boy, girl. Girl, boy, and then girl, because that would represent this one. Okay, and then we have girl, girl, and then boy. And then the last one represents girl, girl, girl. Okay, so now what we're going to do is we're going to look at the sample size. So here's our sample size. We have all of these listed in here. So that means how many do we have? We have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. Okay, so we know that there are 8 possible outcomes. Okay, now for the event E, which is equal to 2 boys and a girl, well, let's take a look at that. Where do we have 2 boys and a girl? Well, we can see here that here's 2 boys and a girl. Okay, here's another 2 boys and a girl. And then here's another 2 boys and a girl. So that means we have 1, 2, 3 that represent the event of 2 boys and a girl. Now, because the outcomes are equally likely, for example, BBG is just as likely as BGB. Okay, so what do we do here? Well, we're going to find the probability of that event occurring. We know that the probability of the event occurring for when we have 2 boys and a girl is 3. And then we're dividing it by the number in a sample size, which is 8. And so that gives us 0.375. So we're going to say that there is a 0.375 probability that a family of 3 children will have 2 boys and 1 girl. Now, if we repeat this experiment 1,000 times and the outcomes are equally likely, having a girl is just as likely as having a boy, we would expect about 375 of the trials to result in 2 boys and 1 girl. Okay, now the way to look at this is that if I convert this to a percent, this would be 37.5%. And so writing this as a fraction is 37.5 divided by 100, because that is parts per 100. Now, if we want to move this over to one more decimal place, we'd have to multiply both the numerator and denominator by 10. And so therefore, we're going to get 375 over 1,000. So that's how we're getting that last statement. Okay, meaning that there's 375 of the trials that will result in 2 boys and 1 girl out of the 1,000. Okay, next, comparing empirical probabilities and classical probabilities. Now, in comparing the results of examples A and B, notice that the 2 probabilities are slightly different. Empirical probabilities and classical probabilities often differ in value, but as the number of repetitions of a probability experiment increases, the empirical probability should get closer to the classical probability according to the law of large numbers. However, it is possible that 2 probabilities differ because having a boy and having a girl are not equally likely events. Now, maybe the probability of having a boy is 0.505 and the probability of having a girl is 0.495. If this is the case, then the empirical probability will not get closer to the classical probability because the events boy and girl are not equally likely. Okay, objective 5, recognize and interpret subjective probabilities. If a sports reporter is asked what he thinks the chances are for the Boston Red Sox to play in this season's World Series, the reporter would likely process information about the Red Sox, pitching staff, leadoff hitter, and so on, and then make an educated guess of the likelihood. The reporter may respond that there is a 20% chance the Red Sox will play in the World Series. This forecast is a probability, although it is not based on relative frequencies. We cannot, after all, repeat the experiment of playing a season under the same circumstances, same players, schedule, and so on, over and over. Nonetheless, the forecast of 20% is equal to 0.20 does satisfy the criterion that a probability be between 0 and 1 inclusive. This forecast is known as a subjective probability. A subjective probability is a probability that is determined based on personal judgment.